All right, so we are going to start 2.7 today. Graphs of rational functions. Two things to learn. Analyze and sketch graphs. And then the new thing that we have are the slant asymptotes. So these are kind of the same idea as your horizontal asymptote. But instead of the end behavior of your graph being horizontal, the end behavior of your graph will approach a diagonal line. And so we'll learn how to find the equations of those slant asymptotes. All right, so a few guidelines for graphing rational functions. First, simplify if possible. So sometimes that could mean starting to factor it so that way you can see more what those holes are, vertical asymptotes, that kind of thing. We're going to plot the y-intercept. So in order to find the y-intercept, you're going to plug in a 0 for your x values. So once you plug in a 0 for your x values, that will give you your y-intercept. You're going to find the zeros of the numerator. So remember, the zeros of the numerator will be your x-intercepts. Find the zeros of your denominator. Zeros of your denominator are either going to be vertical asymptotes or holes. We're going to sketch any other asymptotes. So your other asymptotes would either be a horizontal asymptote or a slant asymptote. And then you're probably going to end up needing to use your calculator. Once you have all of that stuff on your graph, you're still going to use your calculator to graph it so you can kind of see what it looks like and then to fit it all onto the axis. So let's start with kind of a basic one here. We have 3 over x minus 2. So if we first think about this and what our parent function will look like, if we have 3 over x minus 2, our parent function of this is really just the graph 1 over x. Okay. So if we first start by finding our y-intercepts, so remember, to find your y-intercepts, you're subbing in a 0 for all of your x values. So we would have 3 over 0 minus 2, which would give us negative 3/2. But it's an intercept, so we need to write it in intercept form. So we would say 0 and negative 3/2 as our point. And then if we were plotting that, we would plot the point at negative 3/2 for our y. Then if we were to find our x-intercepts, remember your x-intercepts, you're looking for where your numerator equals 0. So numerator equals 0, since our numerator is 3, 3 will never equal 0, which means that there are no x-intercepts. Holes. So holes are where you have the same factor in your numerator and denominator. We don't have any of the same factors, so we would say none for holes. Vertical asymptotes then, when the denominator equals 0. So when x minus 2 equals 0, would mean that's when x equals 2. So if you just set that denominator equal to 0 and solve for x, you get it in the equation form that it needs to be. So then at x equals 2, you'll draw a vertical asymptote in your graph. And then that last thing is that end behavior. So when we're looking at those first terms, if we're comparing a 3 over x, that denominator has a higher degree. So that means that we're going to have a horizontal asymptote at y equals 0. When that denominator has the higher degree, a horizontal asymptote is at y equals 0. And so then we could graph a horizontal asymptote which with horizontal asymptotes, your graphs are actually allowed to cross them in parts of the graph. It's more of just the guide for as x approaches positive and negative infinity and what it's going to eventually approach horizontally. Then once you have everything on your graph, you can either graph it on your calculator to see what it looks like, or if you just know what that graph is going to look like, then you can sketch it and make sure it follows all of those points that you've already graphed. All right. So then when we get to our slant asymptotes for the end behavior, so if you don't have a horizontal asymptote at the end, you're going to potentially have a slant asymptote. And that's going to happen when the degree of the numerator is exactly one more than the degree of the denominator. So what that could look like is if you had an x squared minus x plus 1 over x minus 2. So if we had this kind of polynomial rational function, we notice that the degree of the numerator is 1 more. Right? That degree is 2. This degree is 1. So if it's 1 more, then we're going to have a slant asymptote. And the way that you actually find the equation for your slant asymptote is you do the division. So we have to divide our numerator by our denominator. So when your denominator is just that linear function with a constant, we could use synthetic division. So we could put this 2 on the shelf and then use the 1, -1, and 1. Bring down the 1, 2, 1, 2, and 3. With your slant asymptotes, though, we don't pay attention to the remainder, and we just look at this linear equation right here. So the equation for the slant asymptote would be y equals x plus 1. All right, so then the next slide just takes you through another example of a slant asymptote, what it means, how you get it, just in case you forgot. And then we've got this last one here, and then we'll have a bonus example with how to find the y-coordinate of a hole, just as the reminder. But we're going to go through this whole thing, graph it, and then put it on our graphs. So remember, the first thing that you're trying to find is your x-intercept. Nope, the first thing is usually our y-intercept, isn't it? So our y-intercept, we'll erase that and rewrite it. So our y-intercept is when x is 0. So if you were to plug a 0 in, and you get 0 squared minus 0 minus 2 over 0 minus 1, you would get 2. But because we're writing it as an intercept, we'll write it as the point 0, 2. So then on your graph, you'll plot the point 0, 2 as your y-intercept. Your x-intercept, that's still the thick pen. Your x-intercept, remember, is when your numerator equals 0. So if we were to factor this, it would factor into x minus 2, x plus 1 in the numerator, x minus 1 in the denominator. So just looking at it, we know we don't have holes because you don't have the same factors in the numerator and denominator. Our x-intercepts will be when your numerator is 0. So when does x minus 2 equal 0? And when does x plus 1 equal 0? So we would get when x is 2 and -1. And so writing those as intercepts, we would say 2, 0 and -1, 0. And then we could plot those points. So at 2, 0 and -1, 0. Vertical asymptotes would be when your denominator is 0, but not the same as your numerator, but we don't have those same factors, so we just know our vertical asymptote will be when x minus 1 equals 0, which would be when x equals 1. So again, then we'll plot that vertical asymptote at x equals 1. And then when we look at our end behavior, when we're comparing those terms, we notice that our numerator has a degree that's 1 more than the denominator. So that will be your slant asymptote. And in order to find that equation, we're going to do the synthetic division. We can put 1 on the shelf from the denominator, and then we have 1, -1, -2 from your numerator. We get 1, 1, 0, 0, -2. Remember, the remainder doesn't matter, so we really just have that 1. So y equals x would be the equation for your slant asymptote. So if you were to plot the line y equals x through there, and then if you were to graph it on your calculator, remember when you graph on your calculator and you put it in, your numerator needs to be at a set of parentheses, and your denominator also needs to be in a set of parentheses. And so then when we draw our graph will look something like this. All right, and then our last thing we're doing is that bonus example. Just that reminder of, it's not part of 2.8, but we're just using 2.8 as our place that we're going to write everything down. So if you had a function, oh, I don't like that one. So if we had a function and you factored it and you had x minus 1 and x plus 2 over x minus 1 and x plus 3. And we needed to find the whole, that it was the x and the y coordinate of the whole. Okay. So remember, the x coordinate of the whole is whatever factor is the same. So in this case, the x minus 1s have the same factor. So we know that x equals 1 will be the x coordinate of the whole. So we'll say, okay, the x equals 1 is the x coordinate. We're going to remove it. And then whatever you have left, this x plus 2 over x plus 3 is what you have left. That would be like your simplified function if they asked for simplified. You're going to plug the 1 in for any x's that you have left. So we would say 1 plus 2 over 1 plus 3, and we would get 3/4. So 3/4 would be that y coordinate of that whole.